Oh, let me start with an unusual scenario. Let's imagine you've recently been elected as Prime Minister of the fictitious country of Ruritania. Right? You've wisely chosen me to be your internet czar, and I'm saying, oh, you know what? We're going to do something to raise the morale of the people of Ruritania. We're going to have a pop-up appear on every single website, right? So we have a screen here, and I'm just going to write R for Ruritania because I can't remember how to spell it. We're going to have a pop-up. What's it going to say?
Congratulations, I don't know.
Congratulations for living in Ruritania. Whereas, like, so that's in Ruritania, and here, if you're in Europe, you're going to have a sort of similar pop-up, but it's going to say consent to cookie, yeah. Consent to cookie. Different nations have different laws like this. So in the UK, we've got the OSA, Europe GDPR. Germany has some privacy laws which are pretty strict. Now, let's say you're like Amazon or you're Google, and you're serving a web page, and you've learned that in Europe, if you don't do the cookie consent, you're going to get some massive fines or be banned. And in Ruritania, if you don't have congratulations on living in Ruritania, again, you're going to get a huge fine. You're going to be banned from the vast Ruritanian economy. So the question is, how do Amazon and Google work out that this computer is in Germany and this computer is in Ruritania? Have a guess. What sort of things are you thinking about here?
The sort of modern phone type computers,
all right,
of course, have got GPS, and perhaps we could use that. But usually it says, will you let this website?
Right, okay. Precisely that. So
that's in the hands of the user, right, in that instance.
It's your phone, and to a lesser extent, your laptop. There's a bunch of sensors on there, right? There's GPS. We can tell where a computer is from Wi-Fi. When Google were driving around in their streetcars making maps everywhere, they also took the opportunity, and this was super controversial at the time, they took the opportunity to go, all right, we are in Main Street, and I can see, it says here Sean's Wi-Fi, and now we're in the High Street, it's Richard's Wi-Fi. By knowing what Wi-Fi signals they see, you can also have a good guess at where you are, because they've driven around, they've taken a survey about that. So the Wi-Fi signals, you've got a magnetometer on there, it's detecting magnetic fields. Now that's super useful if you're using Google Maps, right, or Apple Maps, whatever. Because you do want the exact location. You want to know you're going exactly to your location. But as you say, you've got to click on, yes, I actually want this website to really know my location, because you just don't want any website knowing exactly and precisely where you are. So if Amazon says, hey, you're going to consent to knowing exactly where you are, you're not going to say yes.
Yeah, but I think there were people who just click yes on everything.
Oh, that's true. Okay, that's true. That is true. Some people are just going to click yes, but mostly they're not going to be able to find themselves able to comply with this cookie consent and with our new Ruritanian legislation if we use that.
So it's got to be connection and IP related then.
Yeah, you've got it. So you're ahead of the game here. So one thing that we can't prevent them knowing is the Internet Protocol address. So we'll stick with IPv4 because it's simpler. It's not that different than IPv6. And let's have a little look at our old friend, the IPv4 address. So that's 32 bits arranged as 4 lots of 8 bits. So we're going to get, in dotted decimal as we call it, 128.64. I'm giving myself easy numbers because if I want to write that out in binary, it's simple. So there's our IPv4. It's 4 numbers. How are we going to turn that to a location in the planet? And there isn't some secret encoding. In fact, one of the reasons I want to talk about this is it's almost an accident that we can do this at all. It was never the intention of the system that this IPv4 address would be a way that we could trace where somebody is. It was not its purpose. So this is 32 bits. And we could write that out in binary. So 128, as I say, I've given myself an easy one. 1, and then 64 is, hopefully I'm going to get the right number of zeros here. 1, 2, self-doubt sets in. And then I'm not going to write in the rest. Now, to make the internet work, we actually divide this IPv4 address into 2 separate parts. So we have this left-hand edge, the most significant part of it, the kind of high-end bits. We're going to call it the network part. Quite often it will split on these dot boundaries, but not always. So let's imagine we split it here. And we're saying these first 12 bits, if my counting is good, these first 12 bits are the network part, and these 20 bits are the host part. So everything on the planet that begins with this, why have I got a 1 there? Goodness me, I gave myself an easy number and then messed it up.
You were hoping for some comments on that.
Oh yeah, that's it, I was there.
It's engagement.
It's engagement, it's a deliberate mistake. Well done for spotting it. Oh my goodness. Oh dear. Getting back to what we were saying. Anything beginning with this bit pattern, 1 0 0 0 0 0 0 0 0 1 0 0, whatever it is here, that's going to belong to this same network. Okay, and that's really useful. That's a useful property because we need to think now about how we navigate the internet. So we need to think for a moment that all of this Internet Protocol v4 address, it's got to get us around an incredibly large network of routers, or router if you're an American. So some packet comes in here, here's our packet, and here's its destination. And this router here needs to know, do I want to go this way or do I want to go this way? Yeah? It's clearly impractical for it to have an entry on this router for every single IPv4 address. That's just not going to work. We need to collect them somehow. We need to group these addresses. We do what we call longest prefix matching. So we might say everything beginning with this pattern of 12 bits is going this way. But everything beginning with, I don't know, let's say my original messed up version, anything beginning with that goes this way. So we need this way of collecting together IP address prefixes in order to make this problem of routing tractable. So we want the idea that IPv4 addresses somehow collected together, owned by the same people. Now this falls under the purview of several organizations, ICANN, the Internet Corporation for Assignment of Names and Numbers. That's the global, but regionally we have the RIRs, the regional assignment people. And I won't even try and remember what they all are. There's around about 5 of them. Like, there's one for Africa, there's one for North America and Canada, there's one for Europe, Russia, and I think a bit of the Middle East. There's one for almost all of Asia and Australia. So, if you're a new internet company and you say, I want some addresses, you need to pay these people. You need to cooperate with these people. And you'd say, I'm on a lovely Caribbean island. I need some IPv4 addresses for my new internet business. So can I have 16,000 IPv4 addresses? And they'll almost certainly say, no, oh my God, IPv4 address exhaustion, there isn't that many. But in theory, that's how it should work. So these RIRs, these regionals, they are assigning the Internet Protocol v4 addresses. And they're traded like anything because they're a valuable commodity, but they're traded in blocks with a prefix. When we're specifying them, we will use a slash notation. So if we said something is a /16, that means the first 16 bits, or these first two numbers here, are the network bits. So a /16 is bigger than a /17, which is bigger than a /18, all the way down to a /24, which is the first three numbers. You can divide it up finer than that. So this means these addresses are traded in blocks. They're registered with the RIR, and the RIR asks you, oh great, you're a company, you've got some internet addresses, where are you? Yeah? So they've got a database now. They've got a database which is saying, this internet protocol address belongs to the lovely Queen Mary University where we're sitting right now. We're located in the East End of London in Tower Hamlets. So that block of addresses is in Tower Hamlets. So if I contact something from my computer over in the corner over there, then the internet protocol address, the regional registry is registered it to Queen Mary. We know Queen Mary's in Tower Hamlets, and Queen Mary have correctly registered ourselves in the right position. So the database will come back with that as in Tower Hamlets. So how do we then, if we are Amazon or whoever, we're trying to locate it? There's companies that make this their business. There's various of them. I'm going to demonstrate one of them. Others are available. So MaxMind is one I've used a little bit. And their job is to just aggregate all of the databases. You throw them an IPv4 address, and they've got the data of where all of these things are registered. And they'll come back and say, yes, that is in the East End of London. We're very confident about it.
One of our earlier videos was making a traceroute map, wasn't it?
It was, yes.
Was it using some of this data?
It was using this, actually, yes.
Brilliant.
So that traceroute video has got me using that in Python. This may be the first one I ever did with you, I think. One of the early ones, certainly. And that's got me doing that programmatically in Python. Okay, so we've got this idea that we can go from an IP address to a location on the Earth somehow using one of these databases, and the database is held by this regional registry, the RIR. So let's just test something. So I'm working on my Windows machine today for reasons that are very annoying. I've not got my normal Linux machine. So let's take a little path over to Beijing in China. So I'm going to do a traceroute. So this is just a simple way of getting a path from here in the East End of London over to another university I sometimes teach at in the north of Beijing. What it's doing now, it's sending out a series of probe packets, and it's giving us back a round trip time, 3 estimates of round trip time for each hop of that journey. So it's producing a map of the way through the network. And what we can see on screen here, we can see a timing in milliseconds, so quite a short time span. We can also see the IP address, so 138.373.227. So there we've got a 10. A 10 is a local address, not a real address. So this is the first real Internet Protocol address, this 138.373.227. And here, between hop 10 and 11, we see quite a large jump. We see that it's gone up from 16 milliseconds to 236 milliseconds. So that's telling us things have suddenly got a lot longer in terms of time. I'll explain why that is in a minute. So let's start off and let's do something basic. So I'm using MaxMind. Other geolocation services are available, and I've not got a paid account on here, so because I'm being cheap. So here we're asking, what's my IP address? And we can see it's correctly given the IP address, and it's telling us this is in Tower Hamlets in England. It's given us a postcode, and it's actually given us that it's within 5 kilometres. Queen Mary and Westfield College, that's our old name. Maybe we should update that. And it's given us a lat long. So we could plot that on a map, and you've seen me do that before in a video. Let's have a look at some of these other ones. So, saying we can enter some IP addresses here. Let me type in some. So Janet, J-A-N-E-T, is the Joint Academic Network. And we had an address from Janet, 6440.125.57. We have an address from GIANT. So GIANT is the European Academic Network. So clearly we've travelled over from Janet in the UK to GIANT in Europe. So we've got 6040.98.64. So 6240. I'm bound to mess one of these up, aren't I? Now, I said to you when I was doing my preamble that all of the things, essentially with the same initial bits, are likely to belong to the same organisation. So you can see all of these things, 6240 something, seem to be GIANT, seem to be belonging to the international, the European Academic Network. We've got one where the label is Janet and GIANT, so we're not quite certain who that belongs to, but when we pop them into the database, here is where we see, this isn't always, hold on, have I mistyped one? I have also mistyped one. Okay, 6240. Right, there we go. So these addresses beginning 6240, we can see all belong to GIANT. And they're being geolocated to the Netherlands. But we can also see one of them, the one ending in 57, it's got London in its address, so we might be a little suspicious of that. It's belonging to that organisation. It's not necessarily where it actually is. So I said there's this other one where it suddenly hops out to being 200 milliseconds. And that's still the one ending in 102. And we can see that one is being geolocated, again, in the Netherlands. But actually, that one is terrifically further away. It's 200 milliseconds. 236, 239 milliseconds. If we look back at our trace, we can see this hop. And it's also saying Orient Plus, so we suspect that might actually be a lot further away. Mostly this works fine. I've shown you some where it doesn't work, where it thinks something is in the Netherlands. Actually, let's just do one or two more. So we had that Traceroute, and I said that one of the addresses was a Janet address, and it was 146.97.143.217. And that's saying it's part of Janet, the Joint Academic Network in the UK, but Janet has registered itself in Birmingham. This thinks it's in Birmingham, and it thinks it's within a radius of 20 kilometres, but actually, there's no way this traffic is routed through Birmingham. It's just not happening. That's where that organisation happens to be. So mostly this is good to the country level. And you could see that Queen Mary actually put in our proper address and postcode, and it got us pretty precisely. It got us down to actually the right location. It says we're in Tower Hamlets, which is a fairly small area of London. So you know where that one is pretty well. But some of the others we've seen, it's getting the country right, and others, we suspect it's not even really getting the country right. It's saying something's in the Netherlands, and it probably isn't. Okay, now, one thing a lot of people might say is, okay, what if I want this not to be the case? It's locating me to England, and I want to pretend I'm somewhere else. Ooh, that show on Netflix, I really want to watch it, and it's not released in England. That's released in America. I want to pretend I'm in America. So, and a lot of people are already screaming the answer is a VPN. You've got a video on VPNs. I don't really need to go too much into the detail of how that's working, but the basics of it is we're creating a tunnel. We can do this in various ways. But remember, I drew that diagram of the routers in the internet. What we do with a VPN is we create like a passageway so that the first router hop, the first router that our traffic pops out at is in a different country. So a company will buy hardware in lots of different countries and you select. One thing I could do is just hotspot off my phone and see what happens. So I've created a hotspot on my phone. I'm going to connect to that. Now if I ask the question, what's my IP address? Now it's got somewhere completely different. It thinks I'm in Crawley because that's where this BT cellular. So now it's saying my connection is cellular. We've got an IPv6 address. If we use a VPN, we could choose to locate ourselves in more or less any country. There's a lot of ways of doing that initial tunnel. You can hide an IP packet inside an IP packet. You can create an SSH tunnel. But in essence, it's all doing the same trick in different, more or less secure ways of making sure that the rest of the internet thinks that your connection initiates, your connection starts somewhere other than where it actually does start. This geolocation has some strange properties because we've seen it's imperfect, it's pretty good. More than 90% of the time on IPv4, it will be getting you right, I think. But it will give you a lat long. It will give you a precise location on the planet's surface. Now, maybe the company that put the details in, they're certainly not giving a lat long. Maybe they only said, hey, well, we're in America. So now where does it locate? It turns out that locates, if you just say we're in America, then this database will locate somewhere in Kansas. And quite famously, that the place where that locates to, people with not quite as much knowledge as they think they have, think that they've found the person who sent them the threatening email or the person who stole their mobile phone, and they show up at some farmhouse in Kansas demanding their mobile phone back because they've located to a latitude and longitude which is actually just the center of America, and the geolocation only got it as far as America and no further. That's how us, as the government of Ruritania, is going to get a lovely pop-up saying congratulations and welcome to Ruritania every time people browse to us. Here is what's called time to live. Every internet protocol packet, when it's created, is set up with this flag, time to live. It's as if they've all got a doomsday clock on them. We've got a little counter